September 2024, engineers at NASA's Jet Propulsion Laboratory received telemetry from Voyager 1 that should have been impossible. The spacecraft, operating more than 15 billion miles from Earth in the interstellar medium beyond the Sun's influence, detected magnetic field readings that violated fundamental predictions about how the solar wind terminates and interstellar space begins. The measurements showed the magnetic field strength increasing when it should have been decreasing, oriented in directions that don't match any model of the Heliopause boundary, and fluctuating on timescales that suggest dynamic processes no one predicted. Voyager 1 has been in interstellar space since 2012, the first human-made object to leave the heliosphere. For 12 years, its instruments have been measuring this alien environment, and the data has mostly matched expectations. Plasma density, cosmic ray flux, magnetic field topology, all fit within theoretical frameworks developed over decades. But the September 2024 data doesn't fit. And when engineers cross-checked with Voyager 2, which entered interstellar space in 2018 at a different location, they found similar anomalies. Two spacecraft, separated by billions of miles, both detecting phenomena that our models of interstellar space say shouldn't exist. Either the models are wrong, which would require rewriting our understanding of how stars interact with the galaxy, or something is happening in local interstellar space that we didn't anticipate, and that has profound implications for how we understand our cosmic neighborhood. The Voyager missions launched in 1977, taking advantage of a rare planetary alignment to visit Jupiter, Saturn, Uranus, and Neptune using gravity assists. After completing their planetary tours, both spacecraft continued outward, becoming messengers from humanity traveling into the unknown. Their longevity is remarkable. Designed for a 5-year mission, they've been operating for 47 years. Their power sources, radioisotope thermoelectric generators that convert heat from decaying plutonium into electricity, are slowly weakening, but still provide enough power to operate a handful of instruments. Communication with the Voyagers takes over 22 hours for a round-trip signal, more than a light day. Commands sent from Earth take 11 hours to reach Voyager 1. Responses take another 11 hours to return. This vast distance makes the spacecraft incredibly valuable as probes of the outer solar system and interstellar medium, regions we can't easily study any other way. The heliosphere, the bubble of space dominated by the solar wind, extends far beyond the planets. The solar wind, a stream of charged particles emitted by the sun, flows outward at hundreds of kilometers per second, carrying the sun's magnetic field. This wind creates a protective bubble that deflects some galactic cosmic rays and shapes the boundary between solar and interstellar environments. The edge of the heliosphere, called the Heliopause, is where the solar wind's pressure balances the pressure of the interstellar medium. Beyond this boundary, the sun's influence weakens, and interstellar conditions dominate. Before we examine what the anomalous data reveals and why it's forcing scientists to reconsider fundamental assumptions about interstellar space, make sure you're subscribed to Cosmic Outliers and notifications are turned on. The Voyagers are humanity's most distant ambassadors, and every piece of data they send back is irreplaceable. Drop a comment with your theory about what could cause magnetic field anomalies in interstellar space, because the explanations being proposed range from exotic astrophysics to entirely new phenomena. Voyager 1 crossed the Heliopause in August 2012, detected through multiple indicators. The plasma density increased abruptly, indicating entry into denser interstellar medium. The galactic cosmic ray flux, high-energy particles from outside the solar system, increased sharply as the shielding effect of the heliosphere ended. And the direction of the magnetic field changed orientation, no longer dominated by the sun's field, but by the interstellar magnetic field threading through our region of the galaxy. These changes confirmed Voyager 1 had entered a fundamentally different environment. Voyager 2 followed in November 2018, crossing at a different location and providing comparative data that revealed the heliopause is not uniform, but varies in structure and thickness depending on location. For years after crossing, both Voyagers measured conditions in interstellar space that fit expectations reasonably well. The magnetic field strength was approximately 0.4 to 0.5 nanoteslas, consistent with measurements of the local interstellar magnetic field inferred from other observations. The field orientation pointed roughly in the direction predicted by models based on the flow of interstellar material past the solar system. Plasma density was higher than in the heliosphere but matched estimates from astronomical observations. Cosmic ray intensities plateaued at levels indicating the Voyagers were beyond the Sun's modulating influence. Everything made sense. Then, in mid-2024, Voyager 1's magnetometer began reporting readings that didn't fit the pattern. The magnetic field strength started increasing, rising from about 0.48 nanoteslas to 0.63 nanoteslas over 3 months. This is a 30% increase, far larger than any fluctuation seen since entering interstellar space. Simultaneously, the field orientation shifted, rotating by approximately 15 degrees from its previous average direction. These changes occurred smoothly over weeks, not abruptly, suggesting Voyager 1 entered a region with different magnetic properties rather than experiencing a transient event. Engineers initially suspected instrumental issues. The magnetometer is one of Voyager's oldest instruments, operating continuously for decades in the harsh environment of space, exposed to radiation and extreme temperatures. Degradation is possible, but diagnostics showed the instrument functioning normally. Calibration checks using onboard reference systems found no drift. And crucially, Voyager 2's magnetometer, an independent instrument billions of miles away, started showing similar changes weeks later. 2 independent instruments showing correlated anomalies strongly suggest the anomalies are real features of interstellar space, not instrumental artifacts. Theoretical models of the local interstellar medium predict a relatively uniform magnetic field on scales of astronomical units. The Sun moves through the interstellar medium at about 26 kilometers per second, relative to the local standard of rest. As it moves, it encounters variations in density and magnetic field strength, but these variations should be smooth on scales of years to decades. The Voyagers, traveling at about 17 kilometers per second relative to the Sun, move through interstellar space even more slowly from the perspective of the interstellar medium. They should experience gradual, predictable changes as they sample different regions. Rapid changes like the observed magnetic field increase suggest encountering a boundary or structure in interstellar space with sharp gradients, something models don't predict in this region. One possibility is that the Voyagers are encountering a magnetic flux tube, a region where the interstellar magnetic field is locally enhanced and organized into a coherent structure. Flux tubes can form in magnetized plasmas through various instabilities and are common in space environments. But flux tubes in the interstellar medium should be large, spanning light years, and the Voyagers are only tens of astronomical units beyond the Heliopause. Encountering a small-scale flux tube here would suggest structures in interstellar space that current models don't include. Another explanation involves the interaction between the heliosphere and interstellar medium. The heliopause is not a static boundary but a dynamic interface where solar wind and interstellar plasma interact. Instabilities at this boundary could generate waves or structures that propagate into the interstellar medium. If Voyager 1 encountered such a structure, it could explain the magnetic anomalies. But this requires the heliopause to be far more dynamic than models suggest, capable of generating structures that persist tens of astronomical units into interstellar space. Researchers also considered whether the anomalies might be related to changes in the Sun's activity. The Sun's magnetic field varies on an 11-year cycle, and this cycle affects the solar wind and heliosphere structure. The heliosphere expands and contracts slightly as solar activity waxes and wanes. Perhaps recent solar activity changes affected the heliosphere's boundary in ways that propagated outward as disturbances in the interstellar medium, but the timescales don't match well. Solar cycle effects should take years to propagate to the Voyager's locations, and the observed changes happened over months. A more exotic possibility involves encounters with interstellar clouds or density enhancements. The local interstellar medium is not perfectly uniform. It contains clouds, filaments, and voids with varying density and temperature. The Sun is currently moving through a region called the local interstellar cloud, a relatively warm, low-density region, but the cloud structure is not well mapped. Perhaps the Voyagers entered a denser filament within the cloud where the magnetic field is compressed and enhanced. This would explain the increased field strength, but it doesn't easily explain why Voyager 2, in a different location, showed similar changes around the same time, unless both spacecraft happened to encounter similar structures coincidentally, which seems unlikely. The plasma wave instrument on Voyager 1 provided additional data that deepened the puzzle. This instrument detects oscillations in the plasma surrounding the spacecraft, Waves generated by instabilities or disturbances. In September, the plasma wave data showed enhanced activity at frequencies corresponding to electron plasma waves, oscillations of electrons in the plasma. The enhancement was intermittent, appearing and disappearing on timescales of hours to days. Enhanced plasma wave activity suggests increased turbulence or instability in the surrounding medium. This could result from Voyager 1 moving through a region where different plasma populations interact, creating instabilities. But again, the models don't predict such regions near the Voyager's current locations. Comparisons between Voyager 1 and Voyager 2 data revealed both similarities and differences. Both showed magnetic field increases around the same time, September to November 2024. But the magnitude and rate of increase differed. Voyager 1's field increased faster and by a larger percentage than Voyager 2's. The orientations also differed, with Voyager 1's field rotating more than Voyager 2's. These differences suggest the spacecraft are encountering related but not identical structures, consistent with large-scale disturbances or variations in the interstellar medium that affect both locations, but with different intensity. Attempts to correlate the anomalies with astronomical observations of the local interstellar medium have been partially successful. Radio observations of pulsars provide information about the interstellar magnetic field through measurements of Faraday rotation, the rotation of polarization planes of radio waves passing through magnetized plasma. Recent pulsar observations show slight changes in Faraday rotation measures that could indicate variations in the interstellar magnetic field in our region. The timing of these changes roughly coincides with the Voyager anomalies, suggesting a possible connection. If the interstellar magnetic field is genuinely changing, it would affect both Voyager data and pulsar observations. But the connection is tentative and requires more analysis. The cosmic ray data from the Voyagers also showed subtle changes correlated with the magnetic anomalies. Cosmic rays are charged particles, mostly protons, traveling through the galaxy at near light speed. Their trajectories are influenced by magnetic fields. Changes in the local magnetic field strength or orientation would affect how cosmic rays propagate through the region, potentially altering the flux measured by Voyager. The observed cosmic ray variations are small, at the edge of statistical significance, but they trend in the direction expected if the magnetic field changes are real and affecting particle transport. Theorists are exploring whether the anomalies could be related to the structure of the heliopause itself. Recent models suggest the heliopause might not be a simple boundary, but a complex transition region with multiple layers and instabilities. Perhaps Voyager 1 and Voyager 2 are still within this transition region, not yet in true interstellar medium, and the magnetic anomalies reflect dynamics of the boundary layers. But this hypothesis struggles to explain why the anomalies appeared years after the Voyagers crossed what was identified as the heliopause based on multiple independent indicators. Another line of thinking involves the bow shock, a theoretical structure that should form where the interstellar medium piles up in front of the heliosphere as the sun moves through space. Analogous to a sonic boom, the bow shock would be a region of compressed, heated plasma ahead of the heliosphere in the direction of the sun's motion. Early models predicted Voyager 1, heading in roughly that direction, might encounter the bow shock, but observations suggested the bow shock might not exist or is farther away than expected. The magnetic anomalies could be evidence that Voyager 1 is approaching or has entered the bow shock region. But Voyager 2, heading in a different direction, shouldn't encounter the bow shock, making it hard to explain why it shows similar anomalies. The data also raised questions about the nature of interstellar turbulence. The interstellar medium is turbulent, filled with eddies and fluctuations across a wide range of scales. Turbulence theory predicts certain statistical properties for magnetic field variations. The Voyager data, analyzed for turbulence signatures, shows features that don't quite match standard turbulence models. The fluctuations have more power at specific scales than predicted, suggesting either the turbulence is being driven by sources not accounted for in models, or the local interstellar medium has properties that make its turbulence different from what theory assumes. One speculative idea suggests the anomalies might be related to the galactic environment on larger scales. The Sun orbits the galaxy and periodically moves through the galactic plane where matter density is higher. Perhaps the local interstellar medium is being influenced by broader galactic processes, waves propagating through the interstellar medium from distant events, or density variations related to the galaxy's spiral structure. These influences would be incredibly subtle, but might become detectable in the precision measurements the Voyagers provide. Engineers at JPL are planning additional observations to characterize the anomalies better. They've adjusted Voyager's orientation slightly to optimize magnetometer measurements and are coordinating with ground-based observatories to search for correlated signals in astronomical data. The challenge is that the Voyager's power is limited. Each instrument operation requires carefully rationing power. Some instruments have already been turned off to conserve energy for the most critical systems. The magnetometers and plasma wave instruments are among those still operating, but their days are numbered. Within a few years, power will drop to levels where even these must be shut down. Eventually, the Voyagers will go silent, continuing their journey but no longer able to communicate. This makes the current anomalies particularly urgent. The Voyagers are providing data no other mission can obtain. No other spacecraft are in interstellar space. No missions are planned to reach there for decades. If the Voyagers detect something important now, and we don't understand it before they fall silent, we might not get another chance for a generation. The pressure to extract every bit of information from the data is intense. Historical context adds perspective. The Voyager missions have surprised scientists repeatedly. The discovery of volcanic activity on Jupiter's moon Io, the complex structure of Saturn's rings, the strange magnetic field of Uranus, the geysers on Neptune's moon Triton, all were unexpected findings that reshaped understanding. The Voyagers have a track record of finding things we didn't predict. It's entirely plausible that interstellar space holds surprises too, phenomena we haven't imagined because we've never been there before. The philosophical implications are significant. Humanity's understanding of space beyond the solar system comes mostly from astronomical observations, looking at distant objects and inferring their properties from light and other radiation. The Voyagers represent in situ exploration, direct measurement of environments we can't easily observe remotely. When in situ data contradicts remote observations and models, it forces re-evaluation. The magnetic anomalies are a case where direct measurement challenges theory, and history suggests direct measurement usually wins those confrontations. Public reaction to the Voyager anomalies has been muted compared to other space news, partly because the findings are technical and not easily visualized. Unlike images of planets or galaxies, magnetic field data doesn't produce compelling visuals. But within the space science community, the anomalies are generating significant interest. Papers are in preparation. Conferences are scheduling sessions on Voyager data analysis. The next few years will see intense scrutiny of every bit of telemetry from the aging spacecraft. The Voyagers carry golden records, time capsules containing sounds and images from Earth, intended as messages to any intelligence that might find the spacecraft in the distant future. The records include greetings in multiple languages, music, sounds of nature, and a selection of images representing human civilization. The symbolic nature of the Voyagers as messengers from humanity adds poignancy to their scientific mission. They're not just instruments but ambassadors, carrying human voices into the cosmos. That they continue to teach us about the universe while carrying those messages seems fitting. The engineering achievement the Voyagers represent is staggering. They were built with 1970s technology, computers less powerful than a modern smartphone, yet they've operated flawlessly through environments that were barely understood when they launched. They survived radiation belts, extreme temperature variations, micrometeorite impacts, and the slow degradation of components over decades. The fact that they're still sending data is a testament to the skill and foresight of their designers. Every component was over-engineered for reliability. Redundant systems backed up critical functions, and the mission team has improvised solutions to problems that arose over the years, rewriting software, repurposing instruments, and managing power budgets down to the watt. As the Voyager's missions wind down, attention is turning to lessons for future missions. What would a modern interstellar probe look like? It would have far more capable instruments, modern electronics, better power systems, and faster data transmission. But it would take decades to reach interstellar space, even with advanced propulsion. No technology currently available can drastically shorten that timeline without prohibitive cost. Nuclear electric propulsion, solar sails, or even fusion drives have been proposed, but all remain largely theoretical for interstellar missions. The Voyager's legacy is showing that interstellar exploration is possible with patience and good engineering, but also highlighting how far we'd need to go to do it better. Some researchers advocate for an interstellar probe mission, a dedicated spacecraft designed from the start to study the heliosphere boundary and interstellar medium. Concepts have been developed showing such a mission could reach the Heliopause in 15 to 20 years using advanced propulsion and trajectory design. The mission would carry modern plasma instruments, magnetometers, cosmic ray detectors, and imaging systems, providing far richer data than the Voyagers can. But funding such a mission requires convincing decision-makers that interstellar space is scientifically interesting enough to justify the cost. The Voyager anomalies help make that case by demonstrating that interstellar space holds surprises worth investigating. The magnetic field anomalies might eventually be explained by prosaic mechanisms, subtle effects that models missed, or instrumental calibration issues that haven't been identified. Science has a history of anomalies that turned out to be mundane once understood, but it also has a history of anomalies that revealed genuinely new phenomena, from the discovery of Neptune through perturbations in Uranus's orbit to the detection of dark energy through supernova observations. Distinguishing between the two requires careful analysis, skepticism, and willingness to follow evidence wherever it leads. For now, the Voyagers continue their slow journey outward. Voyager 1 is currently about 162 astronomical units from the Sun, increasing by roughly 3.6 astronomical units per year. Voyager 2 is at about 135 astronomical units, traveling slightly slower. At their current speeds, they'll take about 40,000 years to pass within a few light years of another star. Long after they've fallen silent, they'll coast through the galaxy, silent witnesses to the universe's evolution. But for the next few years, while their power holds out, they remain humanity's active presence in interstellar space, sending back data that challenges and expands our understanding of the cosmos. The September 2024 anomalies remind us that the universe is full of phenomena we haven't yet discovered. Every environment explored reveals surprises: the deep ocean, the upper atmosphere, the radiation belts around Earth, the surfaces of other planets, all held unexpected features when first explored. Interstellar space is no different. We're beginning to explore it, and it's showing us that our models, built on limited data and theoretical extrapolation, capture only part of the reality. The magnetic anomalies are cracks in those models, hints that something important is missing. Figuring out what's missing is the challenge now facing researchers as they analyze data from humanity's most distant explorers. If this investigation into the Voyager anomalies and what they reveal about interstellar space captured your imagination, hit that like button and subscribe to Cosmic Outliers for updates as more data arrives and analysis progresses. The Voyagers are writing the final chapters of their historic missions, and every transmission could be their last. Drop a comment with your theory about what's causing the magnetic field anomalies, because this is one of those rare moments when direct exploration is teaching us that the universe is stranger than our theories predicted. We're witnessing the Voyagers' last great discoveries, and they're reminding us why exploration matters.